Thanks a lot, Alex. So, like Alex said, I'm principal engineer at NVIDIA, and I've been our pick, or the guy that's been leading up the effort on getting HDR display into games for the past couple of years. It's been an interesting road, and I'm going to sort of update you on where the ecosystem sits and some interesting developments and where all this is going, and what we can do to make our games better going forward. So, I guess we're going to start off with what is HDR and why do we care? Almost everybody here should probably know this, but it's good to just sort of set a good grounding. It's been in games since about 2005. First definitive thing was Half-Life 2: Lost Coast, and as almost all of you guys know, most titles today render in HDR, just because this is necessary to get a good simulation of lighting within the environment and to produce a nice, believable image. And then rendering in HDR is really, really well understood within the gaming community, but displaying in HDR is still in its infancy, both with gaming and just in general. HDR TVs only became available about 2 years ago. And before that, it was $10,000, $100,000 monitors with all sorts of funky interfaces that were really the only options. And HDR displays are very interesting because they're one of the biggest advances in displays in the past 20 years. It's the thing that you can look across the room and say, wow, that is really different and really unique. So, going back to the high percentage of titles rendering in HDR, I'm going to just assume that, can I get a show of hands? How many people still render without HDR in this room? Yeah, nobody. Nobody renders without HDR. I wanted to say everybody did it, but you never want to assume. So, what makes good HDR? Well, HDR is high dynamic range, and the operative word is range. It's not high. So, it's not about making a brighter image. It's about making an image that it really requires brightness, precision, and contrast, right? And good HDR is going to make your highlights brighter. It's going to make your shadows possibly deeper, maybe not so much depending on where the black level is at on your display today. But it's going to preserve more detail in both of those. And additionally, because we're now going to have more space that we're rendering within and displaying within, we're going to be able to have more vivid midtones. We're not going to have to be kind of crushing them in just to be able to fit our highlights and our shadows. And so we're going to have, they're going to be somewhat brighter, somewhat more vivid. And ultimately, what you're going to get is you're going to get the experience of a deeper image. Now, I hope maybe some of you got a chance to see the BFGD display that we had on our booth in there. You can really, from a distance away, see the sort of difference that HDR makes to a game with that display. So why haven't we been doing this, right? It sounds like a great idea. Well, over the last 20 years, display technology has been mostly stagnant. In that time frame, we did move from CRT to LCD, but for the most part, things got lighter and thinner. The actual colors we were producing didn't necessarily improve. The amount of brightness we were getting out of the display, initially maybe even fell off a little bit and then got a little bit, maybe improved a little bit. And resolution, you think about it, 20 years ago we had displays that were 1600 by 1200. We changed the format to go widescreen, go 1920, but essentially we were talking about the same number of pixels. So we really haven't been improving that rapidly here. And the progress has been slow, and it's all kind of been, as far as color space goes, it's all been tied around sRGB and Rec. 709, which for our purposes today, we're going to consider them the same thing. It's just basically a transfer function that's different between the two of them. But HDR displays really look to change all of this. So let's talk a little bit about just the technology behind HDR in general. HDR display hardware, it's a little bit different, and we have to think about and understand it a little bit as developers, and understand strengths and weaknesses of it to be able to make sure that we're doing the best job for our games, and make sure that when we're reviewing and developing and testing them, we're taking into account what the display hardware that we're working on does. And we also have to think about, we have to, keep some things in mind that, display devices are physical devices. It's not like software, like we're all used to dealing with, right? It's actual hardware. It has limitations on how much power it can put out, how much heat it can dissipate, and, just like the transfer rates over the wires. I mean, one of the early comments I remember hearing from a developer when talking about this stuff is, well, how come we can't do 120 hertz and HDR with 12 bits and full RGB? And well, the answer was, well, the DisplayPort and HDMI interfaces have a restriction on this is how many bits per second that they can do. So knowing the hardware is going to help you understand what these limitations are and maybe help them debug your deal with end user support issues as well. So let's talk about like two of the main technologies with HDR displays today. First of all, we've got our, we've basically got LCD versus OLED in the market. LCDs, we can have over 1,000 nit peak luminance. Some of them, I guess, are getting relatively close to 2,000, but that's fairly rare these days. The best ones have local dimming backlight matrices to allow the best possible dynamic color or dynamic brightness. They get a wide color gamut by utilizing quantum dots, so it gives you very, very intense primaries in a very, very limited narrow band. And that also helps maintain the efficiency of the display. They can suffer from a bit of backlight bleed. And they're generally best suited to bright environments, and they're really well suited for monitors today. In comparison, OLEDs are typically restricted to about 600 nits of max brightness. The great thing is all the pixels are individually controlled and can be completely turned off individually, so you don't deal with backlight bleed. They have good color saturation, so you can actually produce really, really great colors on them. However, they can suffer that color saturation at high peak luminance because they typically have RGBW pixels, right? So they have this white subpixel that if you want to get bright, you're going to be driving the white subpixel that's going to desaturate your color. So they've got the excellent black levels, but because of the lower peak brightness and the really, really great black levels, what they're really best at is a dark or a dim environment. And that's kind of makes them more suited towards TVs. And also they have sort of like phosphor lifetime issues and sort of burn-in issues. So the duty cycle is a little bit different on them. So overall, the end result of this is, as far as technology goes, we're typically going to want to talk about TV versus monitor. TV, hey, this is designed for a living room den. It's designed for a dimmer viewing environment. More limited duty cycle, you're watching a couple hours of TV every night instead of 8 hours in front of the monitor every day. And, typically they also have a lot of image processing to try and get the best out of like an SDR signal. So this means lag, some color distortion. And they're generally HDMI only, which, limits the refresh rate and stuff. And then finally, from a programmer's perspective, TVs are a little bit frustrating because they often sort of obfuscate the information. So EDIDs allow them to report things like what their color primaries are, what their max luminances are. TVs can be a little bit fuzzy about that stuff sometimes. Monitor, on the other hand, this is designed for an office. It produces it handles a brighter environment much better because of the fact that typically it is designed to produce a brighter signal. It has a low latency experience, which it's because it's not doing a ton of processing, and it uses the DisplayPort signal, so we can actually get a higher refresh rate. And in fact, some of the displays we've announced do up to 144 hertz. And then finally, hey, we don't have a bunch of image processing going on, so you can actually have a faithful image out of there. So if you're developing something, an HDR monitor for sort of your gold reference is really a good idea. So since this is a sponsored session, hey, I'm going to say this G-Sync HDR display is actually an example of where we can really go with a good HDR desktop monitor. This particular one that's sort of pictured here, you can see the technology with the backlights, the quantum dot film to get the rich color. This particular breakdown is for the big format gaming display, which is the big 60-inch one that was out there on on the booth. We actually have announced 27-inch and a wide format that's, I think, 32 inches, but I'd have to double check the exact size on that one. But moving on, so we understand the hardware now. Well, what about all these display standards? Well, it's a little bit of an alphabet soup as far as the display standards go. But the reality is a lot of these are all sort of derivations of each other. So we have a bunch of overlapping groups that handle different portions of the pipeline. So, VESA handles DisplayPort and HDMI handles the HDMI signal settings. And both of them, effectively specify out the same signal properties. And they reference off of the Society of Motion Picture and Television Engineers, which specifies out an encoding signal. And then all this, ties back into the, the International Telecommunications Union, which actually handles the Colorspace that we're talking about. So you have all these things that you kind of have to look at a bunch of different specifications to get the whole picture, but they really all do interrelate and interoperate. So HDR10 is sort of the amalgam of a bunch of this stuff. And it's kind of a common term, and it's a little bit misleading because of the fact that it is not a terribly precise term. The original term referred to what's called a media profile that was set up by the Consumer Technology Association. I think they may be involved in running CES. And by media profile, it was kind of designed for what you're encoding on a Blu-ray disc, as opposed to more defining the interface between a PC and a monitor. Today, BT 2100 might actually be a better term for sort of the generic usage of HDR10, because what people generally refer to as HDR10 doesn't necessarily have the exact limitations that the sort of the initial press release of an HDR10 had. So when you hear it in the context of PCs, we're talking about what's called a SMPTE 2084 transfer function, and this is kind of a replacement for a gamma function. BT 2020 color space. 10 or 12 bits per component, so we have high precision, and then the encoding over the wire is either RGB or YCBCR, and with possible chroma subsampling. But those are kind of invisible to you as a developer. So what does this actually mean? Well, on the left there we have a plot out of what are called transfer functions, right? How do we map linear colors to the encoded colors such that they'll display well on a screen? And the really high knee curve in the blue there is the SMPTE 2084, and the green curve is a standard gamma that that roughly approximates what sRGB does. So by having this really extreme knee on this curve, it allows an expression of accurate information with only 10 or 12 bits of data for everything up to 10,000 nits. And there's a lot of color science that's gone into it to determine that this is where humans will have quote unquote a just notable difference between steps and luminance. It allows us to efficiently encode the signal. On the right, we've got this nice curved surface that is referred to as the visual locus. This is basically all of the colors that we as humans can see. Around the outer curve, you've got pure wavelengths of light, basically, and in the middle you have somewhat desaturated colors. The triangles are the gamuts of a couple of different color spaces. The smaller gamut is the sRGB gamut, which is TVs, monitors today. The larger one is actually the BT 2020 gamut, and you'll notice that the corners on the BT 2020 all touch the edges of the visual locus, and that is because they are specified as pure colors of light that you can effectively only produce with lasers. So how does this differ from what we were at? Well, this differs from what we were at because HDR10 the signal is kind of a container format. A game is going to state explicitly that it wants something displayed at an absolute nit level and at an absolute precise color, whereas with sort of the way things work today with SDR, you're saying I want 100% on the red channel, 100% on the green channel, and then it's up to the display to say, well, 100% is 200 nits or 150 nits or 80 nits. And, you know, hopefully your primaries are relatively close to those sRGB ones. If, you know, a display manufacturer decided to make a really, really strong red or something, then your colors come out a little bit janky and you don't really produce the image that your artist really wanted you to produce. So it's not expected that your game or your application is going to fill this whole 10,000 nit BT 2020 color volume, and that's because there's no practical display today to be able to display this. This is a very large format thing that's been designed for growth into. Generally, the target is going to be roughly what's called the P3 gamut, which is a sort of a compromise in between that sRGB and that BT 2020 that was designed around sort of, you know, cinema. And roughly 1,000 nits. That's a pretty good approximation. But we'll talk a little bit about you know, how we can have monitors report their actual values to us and do things with that. But HDR10 operates best by knowing the proportion of this container format that you're going to use as a game. So you're not going to use the whole thing. You're going to use the practical portion that a monitor really wants to display today. And you're going to provide additional information as metadata on what you are actually using. So metadata, you know, it's data about data. And virtually all HDR standards have metadata to sort of express what's called the intent of the signal. And there's two essential types. There's static and there's dynamic. Static doesn't mean static. It means rarely changes. So it doesn't mean never changes. But, you know, it's not something that you would change more than, say, oh, at the beginning of a level or beginning of a cutscene. It's not something that you should be changing, you know, every 5 frames. Dynamic is typically going to be changing constantly. You're actually probably going to be sending an update every single frame. It's obviously you're providing more information in that case, and it often will get referred to in the HDR10 context as HDR10 Plus. That's kind of a marketing term from a couple of TV manufacturers. So importantly, SMPTE, Society of Motion Picture and Television Engineers, came up with this 2086 standard, and then CEA, Consumer Electronics Association, came up with an enhancement on it. It provides, you know, some static metadata that all HDR10 signals really ought to be providing. And it's just basically you're going to tell it what reference primaries that you intended to use are. So, you know, probably going to be telling it P3 in a lot of cases. What your white point was, and you use a D65 white point. That's pretty simple thing. We're gonna stick to the same type of white that we had when we were using SDR. We're going to tell it a peak luminance and a min luminance. So for our reference display, so this is like on our ideal display. This is how much max brightness we ever hit and what our min brightness is. And then there's this content light level and frame average light level that is sort of the absolute peak that we'll ever have in the content, and then the sort of what the average brightness of the brightest frame in the content is. And these allow the display to say, hey, it's staying within my range and I shouldn't do anything to the signal, or wow, the signal is going to be way out of my range, so I have to do some compression to make sure that I'm not, you know, displaying a bad image to the user. And, you know, as PCs, I'm going to talk about what we should be doing about that. So dynamic metadata, it's more information, right? It allows a display to constantly adjust dynamically, like as your scene evolves. So certain scenes are going to be dark and may fit within the confines of the display, and certain scenes may be bright and not fit within the confines of the display. And because of that, you know, it can, you know, slowly adapt the display to be able to sort of get the most out of it. So, you know, if you've got a 1,000 nit signal and you're trying to display on like a 400 nit device, you can probably do a better job if you have some dynamic metadata. And SMPTE 2094 goes about helpfully defining some of this dynamic metadata for us. Unfortunately, it defines four flavors, which actually is kind of a mess for developers, right? Which flavor are you going to have support for in your game? So it's something that's kind of an ongoing challenge, and hopefully this will get cleaned up over the next year or two. Windows, as a result, has kind of taken the position of we're not supporting any of these yet. We're going to wait a couple of years to wait a little while to let this shake out and have dynamic metadata at some point in the future. But games actually should care a lot less about dynamic metadata because dynamic metadata really solves a problem that static pre-baked content has, but dynamic content doesn't necessarily have. We're rendering on the fly. We can select what we're going to do to produce our image dynamically. We don't have to have pre-canned and recorded everything to a disk and have the exact same bits played every time. So we can actually choose our post-processing to have a target luminance that matches what a display reports back to us. And that is really the best thing because we have, since we're generating all this content on the fly, we can have it mapped exactly to what that display is really wanting to do. And additionally, as games, TV shows, movies may be doing a whole bunch of color grading, and movies may go in and individually color grade every frame. Games aren't going to do that because we have a dynamic environment where the user can get into any sort of weird different scenario, and you never even knew what frames could have been there. So there is color grading, but it's maybe a smaller impact on the image. So when you were color grading and trying to hit this one target. Maybe this dynamic metadata is going to help you a bit more, but with what we're doing in games, it's not as much of a deal. So it's there's no real need for you to hope for the display to do the right thing. Instead, what you're going to want to do is you're going to want to do the right thing for your content to a display that is at the level that is reported to you. So I feel the need to say just a quick word on Dolby Vision. Because people will frequently say, "Oh, is it Dolby Vision or is it HDR10?" Things like that. Dolby Vision, Dolby has some interesting technology, and Dolby Vision kind of is I think the right. People sometimes describe it as a standard. I'd say maybe the right word is it's a sort of a proprietary technology / brand, and it does really some interesting things. With the dynamic metadata. Most of its standards are related to all the other HDR10 standards, and it's actually quite similar. But it has some special encoding, and that special encoding, since I'm talking from a PC perspective, that special encoding can be problematic from the PC perspective. And if you are interested in shipping a game and utilizing Dolby Vision as part of your pipeline, you really need to make sure that you're committed for testing to the long term, just to make sure that you aren't having corruption issues tied to some incompatibilities that can arise due to not fully controlling how that display stream goes from the game all the way to the hardware because of the OS limitations. And it's worth noting that basically every device that supports Dolby Vision actually does support HDR10. So you aren't necessarily losing any devices if you say I just support HDR10. Now I believe Dolby is working on resolving some of these issues, but these are issues that I've hit in production, so I want to make guys aware of it. So programming interfaces. How do we get all this stuff going? Well, the Win 10 Creators Update and beyond actually introduces an HDR desktop, which is fantastic. That means we can have HDR in a window. Now, you may need to enable it depending on exactly what build of the OS you have. I think like in RS2, it originally enabled itself by default, but in maybe some later ones, it would typically leave it at SDR by default, and you had to go in and explicitly enable it. And all of this is natively accessible via DXGI, and I actually recommend everyone use the DXGI native interfaces if at all possible, because they are sort of the best way to directly interface with everything. And the way you get at these is, we have some extended output desk colors, color queries. We have, set color space 1, which is going to do some interesting things for, expressing what your color space is. And then we've got, a metadata set function to be able to provide that static metadata. Importantly, these all require an I-flip mode or a flip mode swap chain as opposed to a blip mode swap chain. And if you use the present discard instead of the present flip discard, what you're going to happen is if you're in a window, you're going to end up with truncated data because that blit mode chain will actually blit into a 8-bit buffer before it goes out for compositing. So you'll lose the data and you'll lose your HDR. So you have to actually make sure you create the right type of swap chain for doing this stuff. So as far as the DXGI color spaces, they're a little bit confusing because they're almost like a struct. They have like they have like 5 different fields in them, and they also get overloaded for describing what the display is doing and also how the swap chain is operating, what color space it's in. And like I said, you've got 5 fields. The first one is color space type. For rendering, we're always going to be RGB. You can ignore all the YCBR stuff. That's all just for video. The transfer or gamma function, so it's G22, G10, and G2084. So gamma 2.2 is G22. That's standard sRGB. G10 is a linear format, so no gamma at all. And then 2084 is the SMPTE 2084 transfer function that I showed you earlier. The encoding is going to be either full or studio range. For rendering purposes, we're always going to be in full range. And then we have abilities for like where the chroma subsamples are tied to, whether they're the left or the right. Ignore that because none of that's going to be relevant for rendering purposes. And then the color primaries are going to be either P709, which is sRGB, or the P2020, which is the BT2020 color primaries. So how do we detect that HDR is on? We query ourselves an DXGI output 6. We do a get desc 1 on it, so we've got this extended description. And the extended description, the color space, will give you RGB full, G2084, none, P2020 as its color space if it's in HDR mode. If it's not, you're going to get this gamma 2.2 P709 instead, and that means that you're running the desktop's running in sRGB. Additionally, the new, and importantly, just because the desktop is running in HDR doesn't mean the game has to then run in HDR. You can still run in SDR. The desktop compositor is smart enough to take an SDR image and composite into the HDR desktop. So the additional new display information that comes about is it gives you what the red, green, and blue primaries of the display actually are. Windows has seemingly a database of like some older common displays of what the colorimetry is for those, and then newer displays are typically producing these data straight from the EDID and doing it accurately. And that's an important thing going forward. And it also includes the minimum and maximum luminance. And this is how you can set up your tone map operator correctly for what the ideal maximum luminance for your display is. So this is what the DXGI color spaces look like and what formats that they're actually compatible with. And you'll see that that first one is basically the one that everything has been using for a really long time. And you'll notice that 8 and 10-bit swap chains both default to that mode. There's also 16-bit swap chain or 16-bit per component swap chains that has existed since Vista with a floating point buffer, and these are linear in nature, and those default to that color space, and they have HDR just sort of implicitly. And finally, we can turn on like this HDR10 mode where things are PQ encoded or SMPTE 2084 encoded with 8-bit or 10-bit systems. But importantly, the support HDR, but there's a caveat that I'll talk about in a moment because they're non-default. So we can set up the color space by running a check color space support against a swap chain. You have to actually instantiate a swap chain and call check color space support and sort of enumerate your way through the ones that you might want. And then you can call set color space 1 once you find the one you want. Which one are you going to use? Well, you're going to use RGB10 or the RGBA16 float is my really strong recommendation. And the reason for this is that it works in HDR by default. You You choose this swap chain, you're going to get HDR as long as you have a flip mode swap chain. There's nothing else you need to do. The color space is known as sCRGB or CCCS, the canonical compositing color space. It's what the OS actually uses for compositing the desktop. And its luminance is 80 nits for a 111 so standard white that you put into there would be an 80 nit white, which matches the sRGB sort of specified white level. And that means 1,000 nits is 12.5 on its scale. So you do your tone mapper, you come out with a value that has sort of an implied nits, and you're going to scale it up such that 1,000 is at 12.5 is how you get your output correctly. Interestingly, the color primaries are actually Rec. 709/sRGB. And these are fairly narrow color primaries, like I showed you earlier with the gamut graph. But wide color is completely supported, and we actually support, sort of even beyond the full visual locus into, the imaginary color space, because with floating point numbers, we have negatives, and those negative values are actually valid representations with this format. So why not RGB10? So the reason not to do RGB10 is, well, first of all, it doesn't really deliver on all of its promises, right? It is touted as being conversion free. It's going to save you a bunch of cycles. That's not really reliably true because depending on what mode of display the display is operating in, like YCBCR, is it 12-bit, is it 10-bit, you're going to have possibly a double conversion going on. And if you're in windowed mode, you're definitely going to have a double conversion because it's going to go from this 10-bit format to the FP16, do the composite in the desktop, and then go back into this 10-bit format eventually. Now, some GPUs can scan directly from 16-bit surfaces, and it's going to be, sort of a driver implementation level thing as to whether they run a shader to do the conversion or whether they just use scan, and it's going to, depend on a few different, settings of what the display is doing and all these other things as to which is actually happening. People will, have talked about, hey, it saves memory. Well, it's actually saving like less than 3% of what your frame buffer really is if you actually think about what these numbers are, because you're only talking about your swap chain. So even if you've got, say, a triple buffered swap chain, and you've doubled it in size, and you're at 4K. If you've got a 4 gigabyte card, that's still only 3% of your space. It's not really a whole lot. And then finally, you'd actually be giving up a bunch of precision that you'd have otherwise, right? These displays can run with a 12-bit signal, and the specifications state that if you support a 10-bit signal, you're supposed to support a 12-bit signal on the display. And if you're using RGB10, obviously you're not going to have a 12-bit signal that you can drive. The 16-bit allows you to do that. And you also avoid requantization depending on which formats are getting selected. You requantize, you could have some banding. So, and the final thing is, because this is a default, it is not a default color space for this swap chain format. There are some challenges within the actual Windows DDI where the transition into that color space can get dropped between the OS and the driver. Basically, the driver is requested to go into full screen mode, and when that request happens, the set color space doesn't actually get passed to the driver. So it thinks it's supposed to render an SDR. You say you set color space, so you send basically like HDR encoded data to a driver that has been told by the swap chain transition to full screen mode to go into an SDR color space, and you end up with this desaturated, dim view that your users aren't going to like. You're going to have some QA problems with it. So that's a reason to avoid this for now. Hopefully, in another OS release or two, we'll have all that sorted out. So setting the metadata. IDXGI SwapChain 4 adds the SDR metadata support. It's just basically a void pointer and an enum. and that's so that it could support more different metadata in the future. But right now, the only one it actually supports is the HDR10 metadata that I've talked about before. And then all the colors are actually in this kind of weird XY scaled by 50,000 space. And that's just because that allows it to be stored as integers, and they're kind of using a direct mapping of what the interface specifications at the low level actually do. They don't abstract it out to, you provide a float and they do the conversion. And then interestingly, min and max are scaled by 10,000, although I'm going to make the claim that I believe that that's actually a typo in the DirectX documents, that max is not actually scaled by 10,000. It's actually a scale by 1. So earlier versions than the Creators Update support HDR on NVIDIA as well. Even going back to Win 7, we utilize NVAPI for doing this. Now, there are some restrictions on this. And because it's going to be restricted to full screen exclusive. That's the only place where our driver has sort of full control of the swap chain all the way through to what hits the display. And the challenge here is that D3D12 isn't really compatible with this because it killed off full screen exclusive. It has sort of this special iFlip full screen mode. And so since the driver doesn't have like full control over everything, it's unable to really do HDR prior to the RS2 update. Importantly, NVAPI is still useful even if you only intend to do HDR on Windows 10. And this is because, like I mentioned before, you have to possibly turn it on the in the display control panel to have the HDR on the desktop. Well, NVAPI is capable of detecting when there are HDR screens attached, but it is not turned on. And then if you utilize the NVAPI interface, it will actually turn it on in the desktop HDR compositing mode and exit back when you leave. Now, I generally suggest that you only do this if you intend to run full screen, just because it could be a little bit jarring for the user if you all of a sudden make their desktop HDR just to be able to run in a little window, possibly. But it is something that is available to you, to have your game sort of automatically work in HDR even if the user has turned it off on their desktop. So what are we going to do about making our app? Well, overall goals is produce a good HDR scene referred image, and by scene referred I mean light values are linear to what the light really should be. That means we have to have it properly exposed. We want to be producing intense highlights, deep shadows. And it's important to remember in all this, not all your scenes may be HDR, right? You may have, you'll have probably a lot of scenes in your game that are, but there are going to be scenes in the game where HDR may not actually, be that different than regular SDR, just because, not everything in the world has a lot of bright and a lot of dim. We're going to make sure we preserve our precision through post-processing, which is, not too big of a deal these days. Then we're going to do our color grading in the expanded space, do the tone mapping, and then we're going to make sure we apply a good legible UI, and hopefully we're going to build up some tools for our analysis. So physically based rendering is the solution for producing a good HDR result. It's going to give you good plausible values with respect to your lighting. And it's going to sort of naturally produce the really strong highlights and deep shadows that you're going to want to have for a good HDR. It requires the artist to set things up properly. And that's going to be, you're going to be able to be finding some art bugs, and I'll show you a couple here in a moment, that you might not otherwise see. HDR is actually going to be sort of this great detector for where am I doing something, where the artists have been doing something a little bit wrong, and we've been missing it, and it's been hurting maybe the quality of our visuals as a result, but we just didn't notice it quite so much in SDR. And here's a great example from some sample content for the UE4 engine. This is the Sun Temple demo, and what you'll see here is that the lighting value for the directional light that is the sun is multiple magnitudes above the proxy geometry that is representing the sun. So we basically have this disconnect when we're looking at the image of the sun is dimmer than the highlight on the floor that the sun is producing. So you'll want to maybe have the artist spend some time on the emissive proxy geometry that is representing the light has to have a lighting value that is sort of reasonably in tune with what the energy that the light is actually putting into the scene to make sure that your images stay consistent and coherent in the HDR space. And the visualization I've got here is basically like a logarithmic visualization of data off of a middle gray. So that's the red is kind of 2 steps below the white. So rendering primary is an important part of all this, and you're rendering in HDR, but you say, oh, I'm rendering in RGB. Well, the question is, what RGB are you rendering in, right? Red, green, and blue are specific points within that color gamut that I showed you before. And all of your rendering is going to be relative to which of those primaries that you selected. We barely think about this today because we've been operating in this Rec. 709 sRGB space for so very long that we just kind of are inherently assuming that that's where all of our primaries are. But altering the primaries actually has serious ramifications for your rendering results because color math changes. Color math is hard, right? So if we modulate a green times a purple, right? So we've got a green light falling on a purple albedo surface. Which of those colors is actually the correct interaction? Right? Your artists are probably assuming that it's brown because of their sRGB monitor. Now, if you go and try and compute that interaction with a BT 2020 color space because you're on an HDR system and you get purple, your artists are going to be pulling their hair out. How come, my brown shadow or whatever is now purple? And similar goes for the green and the pink down there, right? Is it a green result or is it a brown result? So these are things that you actually have to very carefully think about and have a proper reference for your rendering primaries. So the best practices there is use a consistent set. Make sure that you understand what set you're using and always stick to using the same set no matter whether you're rendering HDR or SDR as the final output. Wider primaries are nice because they're going to allow you that production of a wider gamut, right? The way color modulation works is that you're going to be stuck within this positive subspace that is defined by bounded by the primaries. So you're going to be able to produce even potentially more correct color interactions by using a wider gamut space overall. But that will generate colors outside the Rec. 709 sRGB color space, even if you start with all of your colors within that space, because as you get different interactions, you can have, say, a screen space reflection of a red object onto, a red albedo object, and that will get, even deeper red, and because of that, you'll actually, move further, you'll move outside of the sRGB color space, even if everything was originally specified within sRGB, if you do the math in the wider space. So, the conservative choice is actually to stick with sRGB Rec. 709 primaries and do all of your mathematical operations there because you're going to be consistent and have compatibility with the SDR systems that you've got right now. But I'm going to actually suggest that you might want to consider doing some gamut mapping to be sort of enable better use of the wide gamut because these wide gamut rich colors allow us to visualize a lot of colors that that we see in nature, but we just can't show on these SDR monitors that we have today. And getting a wider, richer color game is something that is going to be kind of interesting. I'll talk about gamut mapping in a moment. So, what does our classic post-processing pipeline look like? In general, we're producing a nice scene-referred image. We're going through some generic post-processing, getting an exposure level out, tone mapping everything with respect to that exposure. We maybe do a color grade, and then we composite our UI straight into the frame. HDR-Aware post-processing pipeline probably should look a little bit more like this. We're going to do some scene-referred image processing, then we'll do some general post-processing, which might include some lens blur, motion blur, things like that. We'll apply our exposure, and then we're going to color grade after we've applied our exposure. And we're going to do this in the high dynamic range or wide color space. And then we're possibly gamut map here too to maybe stretch out our colors a little bit and get our richer colors. Then we're going to do our tone mapping. And finally, we're going to actually probably render our UI off screen to a separate sRGB buffer. We're going to keep our sRGB UI. and then go ahead and use the fact that we've got some pre-multiplied alpha in there to do a separate composite, and then possibly format convert if you, say, need to support an HDR10 output for maybe a console or whatever. So we're going to keep everything in sRGB flowing through, or sCRGB flowing through all this till we get to that last step, and then put it all together at the very end, right? So color grading. This is actually one of the tougher challenges we face in HDR, and just because of the fact that people have gotten really tied into this Photoshop LUT-based color grading scheme where they're frequently, even performing it in the gamma space, and this space is just somewhat wrong for the HDR space. Now, I know some people have managed to sort of do a little bit of inverse mapping on this, but it can be kind of challenging because artists have sort of free range in Photoshop to do whatever they want once they're given a LUT that's just sort of, tacked into an image, and you can do a lot of things that are sort of challenging to utilize in an HDR space in that case. Like I've had some developers say, oh, well, we added this complete inversion of the frame, right? And that ends up looking really, really weird in HDR space. So ideally what we're going to do is we're going to do our grading to a scene in the scene referred space before the color, before the tone mapping. And we want the grade to apply to all the targets, sRGB, HDR, ideally, right? So we're actually going to hopefully try and get one grade on everything. And a pipeline that I'm going to talk about in a moment called ACES, the Academy Color Encoding Standard, refers to this as a look modification or a look modification transform, which we're trying to achieve an equivalent look across all of our SDR and HDR results. So that's we want to apply a sort of LUT here. This can be done as a baked out LUT, sort of in a logarithmic space. Or we can do it as pure math, like gamma functions, scales, things like that. So I want to talk about gamut mapping because wide color gamut is something that we aren't getting a whole lot of yet, and it's something that a lot of people are going to potentially want to have in the future. It's the process of moving one color space to another. Now, all of these color spaces I've talked about today are technically just a matrix transform away, mathematically. But that means that you're keeping the same, true color if you use that matrix transform, and that's the thing you should do when you're moving your colors between the transforms. Because if you just reinterpret them as if they were different primaries, all you're getting this very odd stretching of the gamut. Now, if you do just that odd stretching of the gamut, what's going to happen is your hues are going to end up shifting, and your artists are going to say, why are my colors all wrong? And frequently, you're going to be producing a bunch of colors that are probably too intense, with respect to what you wanted. And the last one that is most easily noticeable is that skin tones will become overly red. Skin tones are this brownish color with a little bit of red to it. And if you then proceed to stretch everything and make everything more vivid, it looks like everybody just got a sunburn. And this is problematic from a human vision standpoint because we have this concept in our mental model that is referred to as memory colors, right? Humans are very good at sort of identifying certain colors that we encounter on a daily basis, like the tone of skin. And if we do odd gamut stretches like that, we can end up making things that look disconcerting to our players. So there are basically three solutions to this. Don't expand anything. Just keep the colors as sRGB, if you rendered in sRGB. The second option is to do a soft expansion. Basically, desaturated colors are going to be preserved, but then you have a sort of a Gaussian weighting function or whatever that's going to, as you got to the most saturated colors, move more rapidly out to the larger gamut. And then the last one is, well, if you've got a great artist around and you've got the right tools, just go ahead and let's have an artist generate ourselves a LUT that's going to manage the gamut mapping for us. So tone mapping, we need to select an appropriate tone mapper for HDR. And what you're seeing here with the different curves here is where midtones are going to lie within different spaces. And if we use a standard, a Reinhardt operator or a general SDR, LDR sort of tone mapper, you see that what's happening is, the things that are relatively dim in our scene becomes super bright if we just apply that and say, 0 to 1 is, 0 to 1,000 nits, right? We end up with things that are really overly bright and don't really give us that deep image look that we want. What we need is a tone mapper that is being very, very careful about how it's using that extra brightness and sort of is basically stretching out the midtones. And what that's going to do is it's going to help us preserve detail, right? So if we move from an LDR style tone mapper to, I've kind of got a simulation because obviously I can't, give you an HDR image up here. If we move to an HDR sort of image, you see that, like the detail in the bricks in that highlight region becomes much more visible. We're maintaining that because of the fact that we've got a tone mapper that's not like jacking things up right into the highlight region. So, choice tone map operator, ultimately there's a whole bunch of choices, and it's up to you. Personally, I'm going to tell you right now, local tone mappers I don't think are a very relevant choice for HDR, and it's primarily because local operators are sort of attempting to make up for what SDR is dropping off. Filmic operators are generally a recommended choice today. Most people seem to be gravitating towards the filmic operators, and that's partially because there's 100 years of science and art behind what film does. You get this nice sigmoid-like curve that's actually very similar to the response curve of the cones in our eyes. So it sort of works towards reproducing the same sort of response that we experience in everyday life. Like I have trouble seeing a large part of the audience because I've got these nice bright lights up in my face, and they are driving me into this sigmoid response where I'm having trouble seeing like sort of at the bottom level of the lighting that I see to myself, right? And ACES, this Academy Color Encoding System that was developed by people in Hollywood, is actually a pretty good choice, and it has these adaptable luminance ranges that I'm talking about. So what does the ACES pipeline look like? Well, it's this film production pipeline. It's been driven by the Academy, the people that put on the nice fancy award show every year. And it includes color grading, known as the look modification transform. But it also has tone mapper. It has selectable tone mappers or configurable tone mappers for different levels of illumination. Now, it's an evolving standard. 1.0 has sort of discrete levels of illumination and somewhat hard-coded transforms that are referred to as output device transforms. They're working on advances on it right now that has a complete continuation of it, and you can actually get more information at acescentral.com, where a lot of the discussion and development goes on. But it's a really great foundation to build from, even if you don't want to go directly to something like this. The good news is, you can bake it into a LUT, and it's relatively efficient. So you look at some of these transforms, and you're like, oh, this is going to be way too expensive. But in reality, you just bake it into, a 16 cubed LUT within the PQ or logarithmic space, and it sort of ends up being very efficient for you. Now, I will say right now, it's not the only solution. There are some people that say, I'm just not a big fan of the look of it, even though a large amount of movie making is heading in this direction. But it's at least a great place to start if you have some objections to it. And if you don't have a bunch of time to go out and research and create your own tone map operator, honestly, my advice is why reinvent the wheel? This is pretty good, and a lot of high quality production people have been gravitating around it. So, user interface. Next to the last thing I want to really talk about today. UI is a special case for HDR. UIs are traditionally developed in an image referred space. So like they're written straight in this image, this space of like, this is exactly how it's displayed on the screen. And you're typically using Painter's algorithm into the frame buffer. So we want to be able to preserve, the intent of that UI and not, distort it horribly in the process of moving to HDR. And often you've got, some things like transparency, alpha blending that you're going to have to account for. For HDR, the first thing we're going to want to do is we're going to set an appropriate luminance level, right? So, as I said, sCRGB sets 80 nits as its default white level. Almost none of you have your monitor set right now for 80 nits as its maximum white level. You probably have it set to 150, maybe 200 nits with the brightness control. And that's what most of your players have things set to. I find that what you're going to want to do for displaying for a UI on HDR content, because the content has now possibly gotten a little bit brighter, you want to aim for 300, maybe 400 nits as the luminance level that you set it to. So if you've got sRGB as 1.0, it's stored in your UI textures, when you're going to composite them, you're going to end up scaling that by around 5x to be able to get you up to 400 nits as that white level. And that's a level that will be still comfortable for your viewers, but easily able to be seen, right? You don't want 1,000 nit white, because that's going to, you throw up a big white dialogue, that's going to be quite uncomfortable at 1,000 nits. And ideally, you want to expose a user control for this to be able to, for them to fine tune to what they really find as comfortable within their environment. And also, you're going to want to provide a little bit of contrast control there as well, because as not all of you may know, sRGB, the encoding versus how it's actually supposed to be decoded for the display, the functions aren't quite inverses of each other. So you end up with a slight power function going on with the data that you sent into the display, and this is actually giving you a contrast enhancement that is going to be relative to what your surrounding brightness is. So what are the problems? Well, this UI transparency problem is the single biggest issue that you're going to run into. If you just scale things into a proper level, things will look reasonably right, but that cannot account for transparency. And the reality is, a 1,000 nit highlight can glow through just about any level of transparency that you have. You're 99% opaque. 1,000 nit highlight is still going to really be able to bleed through that. So what we're going to do for UI transparency is we're going to want to do a UI composition pass. So we accumulate all our UI into this sRGB buffer, and we're going to preserve a meaningful alpha channel for it. And then we're going to run a full screen pass to composite the UI. And it's going to detect where we have a non-zero alpha, and it's going to apply a tone map operator to the HDR data. And it's just going to be a simple tone map operator. It's going to be x over x plus 1 for just the luminance data. And that's going to allow us to scale everything back into a 0 to 1 range for that HDR data. And we'll scale it back up to the UI white level. And now it's at a level where you can safely put the UI over top of it. Now, additionally, you might want to have a little bit of care, of a response curve on the alpha as it goes from like 0 to 25% transparent or whatever, just because you'll see a little bit of oddity if you have a flicker alpha that goes all the way to 0, because you'll sort of suddenly turn on the tone mapping. So you might want to have a soft transition into that tone mapping. And then finally, you actually want to make sure that you remap your HDR color space into its native color gamut before you do this luminance transform with the tone mapper, because that avoids having negative values if you've gotten wider gamut than the sRGB space, so that you don't end up with any division by 0 issues there. So finally, we want to build some good tools. You want to be able to visualize in your engine what the range is. Here is again a visualization of the ranges, and I'm actually using the actual scene referred data and visualizing the scene referred data here with respect to luminance. You can see we've got really nice bright sky, but we don't have a lot of shadows going on. This is actually an image from the kite demo that Epic did a couple of years ago, and this is actually one of the interesting things. Is like, hey, everybody says we look at this demo; it's a fantastic demo, but this sort of underscores how sometimes even fantastic demos don't necessarily have a fantastic amount of range just because of how the scene is set up, right? So there's not a ton of range here because they don't really have any good deep shadows. And so, this will improve somewhat with HDR. It'll get more colorful, but you won't necessarily feel like quite as much of a growth in depth as some of that Sun Temple stuff. And Infiltrator is a fantastic example that I've done a lot of work with, just demonstrating it in HDR. And for full reference here, when I've done these things, I haven't changed anything within the source content. As long as the source content is doing a good job in its physically based shading, it's going to produce the good values that are going to produce good HDR out. So do things like this. It'll help your artists visualize what's going on and tell them, what they're doing wrong. Help them visualize, hey, where a particle effect is too dim or too bright, and all these other things. And I'd like to thank you guys all for coming. And I might have a minute or two for questions. Actually, I hit my time, but we have a half hour till the next session.